Muhammad, and this is a new kind of video for our method of consistent deformation. This is going to be part 5. Let me use the okay, this is part 5, and I'm going to talk today about the support settlements. This is my speech, or maybe the topic for today. Okay, so the method of consistent deformation in general, it is already have explained, or I have explained it in the maybe last 3 or 4 videos. Today we are going to talk about something that is really important and also relevant to the method of consistent deformation, which is related to the support settlements. Okay. So now, first of all, we need to think about the support settlements, why they are occurring in the first place. So support movements due to weak foundation. This is the main reason, as you can see, due to weak foundations and the like may include significant stresses in external indeterminate structures and must be considered in their design. Because we are talking about indeterminate structures, this means that we are going to find that our structure is not going to tolerate any kind of deformation or movement due to the weak foundations. So this is why in case of indeterminate structure, it is very important to consider this support settlement or movements in general. Okay. Support settlements, however, do not have any effect on the stress conditions of structure that are internally indeterminate but externally determinate. Yes, because this is an important issue we need to think about, that we need to differentiate between the internal indeterminacy and the external indeterminacy. We want to differentiate between the two, because actually whenever we are thinking about the internal indeterminacy, support settlement have nothing to do with it. It's only taking or we are highly concerned with the externally indeterminate structures, because in this case we are going to find that there is something, or there is additional stresses going to happen. So this is why support settlements, however, do not have any effect on the stress condition of structure that are internally indeterminate but externally determined. Okay, so our main point is our structure should be externally indeterminate in order to find some effect from the support settlements. This lack of effect is due to the fact that the settlement causes such structures to displace and or rotate as rigid bodies without changing their shapes. This is the reasoning behind that we are talking about this point. We're saying that for externally determinate structures, we do not have any kind of stresses. Why? What is the reason? Because this rigid, there is a kind of rigid body motions. Okay, so whenever that we're talking about rigid body motions without changing their shapes, means that there is no additional stresses that is going to be induced due to this support settlements. Okay, the next is the method. The method of consistent deformation can be easily modified. So here we can modify our method to include the effect of support settlement in the analysis. Okay, so we are going to talk about this part, how to apply our support or our consistent deformation principles that we have already studied before on the support settlements. Okay, now let's have an idea about the concept itself and how it works, and then we are going to talk about the details through an example. Okay, so first of all, consider, for example, a two-span continuous beam subjected to a uniformly distributed load W as shown. Okay, so here we have our structure here, as you can see. This is like we have 1, 2, 3, and 4 supports. One of them is hinge, and we have, as you can see here, this is 2 supports. We have at B only 1 support. This means that 1 reactions. here 2 reactions, 1 support, 2 reactions. Here 1 support, 1 reaction because it is roller. Here it is roller and we have 1 reaction. Here it is roller and we have 1 reaction. So we have By and Cy and Dy in addition to Ax and F and Ay. This means that we have like twice statically indeterminate structure. And this is similar actually to what we have explained before in 1 or 2 videos, maybe 2 videos before. I have explained about the same example exactly. Now let's talk about how we are going to use our consistent deformation method in the support settlement issue. So first of all, suppose that the supports B, which is supports B and C of the beam, undergo a small settlement. So at B and C, we are going to consider that they are like experiencing small settlements. In general, support settlements, they are small in general. We are not considering something large. So this is something commonly to be used, which is small settlements. So delta B and delta C, respectively, as shown in the figure. So this is small settlements at B and at C. To analyze the beam, we consider the vertical reactions By and Cy to be redundant. So we are going to consider this By and Cy as our redundants. Okay, so our consistent deformation is going to be like removing this restraint here and saying that there is some settlement is going to take place and there is reaction or redundant is going to be used in order to maintain equilibrium at these 2 points. Okay, thus supports B and C are removed from the indeterminate beam to obtain the primary beam. Okay, so we need now to see what is the primary beam that we are going to talk about. Okay, let's have the next slide. So here, this is our next slide here. So as you can see, this is the indeterminate beam. Already we have seen this in the previous slide, and this is the primary beam subjected to external loading. So as we said, we removed the supports here at B and the supports at C, and we said that they are going to undergo this kind of small settlements. So we are actually, this is the small settlements, I'm sorry, and now this is the primary beam subjected to the external loading. The primary beam subjected to the external loading. So we have only our external loading here, which is W, and we have the distributed load. And after the removal of the restraint at point B and point C, we are going to find that there is a kind of displacement due to the original load. So we're going to talk, or we're going to say that this is delta B node. As usual, and as I said it before and many times, delta B, the first letter means that the displacement at this point, and the second letter, which is O or node, it is due to external load here, or due to something here. So here this is displacement. This here, it is due to the external load. Our case, it is the external load is distributed load. Similarly, delta C O means that the displacement at point C due to the original loading here O. Okay. Okay. So that's the case. So we have chosen the primary beam, okay, which is going to be removal of the restraint at point B and point C. After that, we are going to load the primary beam with the external loading, which is the original loading that we have, okay? And then we are going to put our system, we are going to say that the indeterminate beam equals to the original system loaded with the external loading plus 2 additional systems, okay? So the first one is going to be the primary beam loaded with redundant by. So we have, as we said, we have the redundant here, which is by. We are going to use it, we're going to use by as our redundant. This means that we are going to use the primary beam and we are going to put 1 unit load at point B, as we have done many times before. And then there is displacement going to take place at this point, point B. It is the flexibility coefficient, FBB. FBB, as we said many times, F means that flexibility coefficient, it's displacement, for example. B means that it is the first subscript. B means that the displacement at point B, and the second subscript is due to load at point B. So we have 1 unit load here applied, and we're going to find that we have the flexibility coefficient FBB is going to be in the same direction, as you can see, of the applied unit load. That's well. What about the point C? We're going to find that point C is going to experience FCB, similar in a similar fashion. So we have F, this FCB. So the meaning here is the displacement at point C due to unit load at point B. Okay, so this is the unit load at point B, and this is the displacement at point C. This system is going to be multiplied by, as you can see here, by the redundant itself, which is by that we are talking about. We have the reaction here, which is this reaction. Okay, we have this reaction. Okay, so now let's go to the next part, which is the next system. The primary beam loaded with redundant CY. How we are going to make it? Simply, we're going to say that we're going to apply unit load 1 at point C, and there is kind of displacement. We call it FCC. You understand it now, the flexibility coefficient at C due to unit load at C. And there is additional type of displacement that is going to take place at point B, which means that the displacement at point B due to unit load at point C. This system is going to be multiplied by exactly the redundant CY that we do not know it, the redundant CY, which is this one. Okay, so we're going to multiply it by CY. So this is our case now. Our indeterminate beam is going to be the summation of 3 systems. The first one is going to be the primary beam. The second is going to be the first one is going to be the primary beam loaded with the external loading. The second is going to be the primary beam loaded with unit load at point B. And the third is the primary beam loaded with a unit load at point C. Okay, this is our philosophy now. So from here we can say that we are going to have the Comfortability Equation. We're going to have the Comfortability Equation. So let's have the clear this kind of annotations here. So I think that it doesn't work. Okay, so anyway, so this is, let's have one slide back, yes, here. So in this case, you're going to find that we can apply our Comfortability Equation. The Comfortability Equation is going to be applied. Now, okay, how we are going to apply our Comfortability Equation? We're going to say that every Comfortability Equation should be used at one of the points where that the redundant has been assumed. So we assumed at B and C, right? At B and C, we assume that our redundance here, which is BY and B and CY. So we're going to apply our first Comfortability Equation at point B. So let's write it together. So we are going to say that the displacement due to external loading at point B on the primary beam, which is this one here, this one, it is going to be plus the flexibility coefficient at point B due to the redundant BY So this is multiplied by this one. So it is going to be FBB, the coefficient or the flexibility coefficient, times BY, the redundant, plus the redundant or the flexibility coefficient at point B in the third system here when the load is being applied on C times CY. So we are going to multiply them together in order to counteract the main effect of the external loading, right? So we're going to put it here, FBC, which is this one, okay? And this is CY, which is this redundant. Then they should equal to, yes, here is the point. This is not 0 as we used to do. Before it was 0. If you remember the previous videos, we use this value to be 0. But actually here, it's not 0. The displacement at the original indeterminate beam, here, it is not 0, right? It is delta B. Delta B. It is delta B. This means that the original settlement. It is the original settlement. Take care. It is delta B. Delta B. In a similar fashion, we're going to apply the second Comfortability equation at point C. So we're going to talk about point C as you can see it here. We're going to say that the displacement due to external loading, which is delta C node, plus the flexibility coefficient due to unit load applied at point B, multiplied by the redundant BY, here, plus the flexibility coefficient at point C due to unit load applied at point C multiplied by the redundant CY, which is the third term, would equal to delta CY. What is delta CY? Exactly. Here it is delta CY. We're talking about settlement. It's not 0. This is not 0 as before. Before we used to put it 0. But here we are not going to put it. It has a value. It has a value. Okay? So these are the two Comfortability equations that we are going to use. The right hand side no longer equal, okay? The right hand side no longer equals to 0, but is equal to the prescribed values, settlements, and the supports. This is what I have explained shortly, okay? So take care of this. This is the main idea of the support settlement, that we are going to use the same philosophy that we have used before in solving the different system using consistent deformation, but instead of having the right hand side to be 0, it is going to be value. It is going to be numerical value, which is the settlement of the supports at point B and point C, or whatever the support that we're talking about. Okay? So that's what we are going to see in an example. Okay? I hope that you have understood now what is the rationale behind the point of the support settlement and what is the difference in regarding the Comfortability equation and how we can apply our primary system, how we can apply the external loading and the redundant, okay, and the unit loading in each case. Okay, now there is hints that we need to understand. There are some hints that we need to understand before going into an example. I'm going to talk about the displacement magnitudes and sign. This is important actually. We can talk about the sign convention as well. Although support settlements are usually specified with respect to undeformed position of the indeterminate structure, the magnitude, take care of this word, magnitude of such displacement to be used in the Comfortability equations must be measured from chord connecting the deformed shape. What is the meaning of this? Take care of this because it's very, very important. Chord connecting the deformed shape of the supports of the primary structure to the deformed position of the redundant supports. What is the meaning of this? Let's have a look here. Actually, we are interested in general, if we're going to say that this is our original beam, which is the beam that is going to be our indeterminate structure, and this is the elastic line after the displacement or the support settlement. So we are going to say that, what we are going to say is that we are going to link between the first point, okay, and the last point of the indeterminate structure with dashed line, as you can see it here. This dashed line, we're going to call it chord of primary beam. This is the chord of the primary beam. Remember that our primary beam now, it is actually as if that it is supported at A and supported at D. It is supported at A and supported at D, right? So we are going to link between the two. We're going to link between A and D, between A and D. And this dashed line is going to be, we're going to call it the chord primary beam. Then our support settlement at B, there are two different types of settlements. The first one is delta B, which is the absolute settlement. But in our calculations in consistent deformation, we are not interested in the absolute, because all of the structure, all of the points, they are going to settle if the whole indeterminate beam is going to move down. Okay, so for example, let's give this as example. So if we have a beam, something like this, okay, or it's hinged here and roller here, and we have something here. Okay, so if we say that it is going to settle like this horizontally, it is the same. I mean that it is the same. No change or no relative change between the supports themselves. This means that there is nothing happen here. Nothing. There is no induced deformation or strains or straining action. So no need to use the consistent deformation, because all the supports, they settled with the same value. So this is what we call it rigid body motion. Rigid body motion. This means that no strains are going to be developed. Okay, but the problem is if one support like A moved with the delta A, and the adjacent support at B, it moved with delta B. So we are interested in what? In the difference between the two. The difference between the support settlement at A and the support settlement at B. So this is what we call it here at B. As you can see, it is measured from this point to the chord. Okay, this is delta BR. Okay, and if you go to C, you are going to find that this is the chord, and we have delta CR. This is the relative displacement or settlement. We're not interested in delta C. We're interested in delta CR, relative. The R here means relative. Okay? Okay. So our comfortability equations in this case is going to be, this is the comfortability equation, FBB times BY plus FBC times CY. This is common and you understand it very well. And what is the right hand side? This is our main concern. Exactly. It is delta BR. Delta BR, if we're talking about B, we're going to talk about delta BR, not delta B. Okay? And if we're going to talk about point C, we're not going to talk about delta C, but we're going to talk about delta CR. So this is the comfortability equation. The left hand side, it is the same as we know. But the right hand side, this is the important thing, which is delta CR. It is the relative displacement, the relative settlement. Okay? It is the relative settlement. Okay. So this is the case, and this is how we are going to perceive our support settlement in case of differential settlement. So the first thing is to link a chord for the primary beam from the point A and the last point, which is point D, for example, and anything in between we can get its relative relative settlement. Okay? Okay, now let's go to previous one. So actually this paragraph, you need to read it again because we are talking here about the first part here, which is the magnitude. We're talking about the magnitude. Okay, this is related to the magnitude. So cord connecting the deformed position. Okay, as we have explained. The second hint that I put it in under this title is the sign. What is the sign? Positive or negative? Okay, the sign. So any such support displacement is considered to be positive if it has the same sense as that assumed for the redundant. Okay, this is because only the displacements relative to the cord cause stresses in the beam. Okay, that's very important hint about our sign. What we're saying here, as any such support displacement, which we mean that the relative displacement as we have explained here, is considered to be positive. Okay, positive. When, if it has the same sense that the assumed for the redundant. So if we have the redundant to be upward and we found that the support settlement is going downward, then our displacement is going to be negative. Okay, because it is different, it goes down here. This means that it is different than the assumed redundant direction. I'm going to explain it in the example shortly. Okay, so don't worry about it, you're going to understand it. Okay, now let's go to the example and see how we're going to apply what we have learned up till now. Okay, so we are going to have an indeterminate beam, as you can see. It is hinged at A, so we have like two unknowns. Roller at B, one reaction here, one reaction at C because it's roller support, and we have one reaction at D. Okay, so we have 1, 2, 3, 4, 5. This means that our indeterminate structure is twice statically indeterminate. Okay, so our beam, as you can see here, this is our beam. It is loaded with external loading of 2 kips per foot, and it is given for us the Young's modulus and the inertia for the cross sections, and we have the length, which is equal length, 20 feet each for each span. We want to draw the shear and bending moment diagrams for the 3 spans continuous beam shown. Due to, what is the main reason? Due to what? Distributed load, and so we have here the external loading is being applied, and due to support settlement. That's the point. We found that there was a support settlement which is 5/8 inch at point B. So point B goes down 5/8 inch, and 1.5 inch at point C, and at point C 1.5 inch, and 3/4 inch at point D, and at point D we found that it goes down 3/4 inch. Okay, so we need to use the method of consistent deformations in order to draw shear and bending moments. Okay, we want to know how we are going to use our consistent deformation method for obtaining or for the drawing of the shear and bending moments. Okay, now let's go to the first step. Our first step is primary beam. We want to find what is the primary beam for our structure. We said before in the previous slide that we are dealing with a twice statically indeterminate structure. This means that we have like 2 unknowns needs to be removed. As usual, we like to remove the internal restraint and use the reaction at point B and the reaction at point C as redundants. Okay, so we are going to use our primary beam, as you can see here in this shape. This is the primary beam, where that we have only hinge at point A and we have roller at point D, and we do not have any restraints now at point B or point C, as you can see. Okay, this is the primary beam, and we are going to apply the 2 kips per foot as distributed and externally load on the beam. Okay, subjected to external loading, as you can see. Okay, so the vertical reactions By and Cy at the interior supports B and C respectively are selected as redundants, and this is already I have said. Okay, then we're going to remove the roller supports at B and C are then removed to obtain the primary beam shown, as you can see. This is pretty similar to what we have explained before, as I said. So now let's go to the important thing, which is, yes, support settlements. Let's analyze our support settlements. I said that the total displacement at, or the total support settlement at point B is 5/8 inch. This is the total one, the absolute. And at point C, the absolute, if you remember, 1.5 inch. And at point D, the absolute was 0.75 inch. Okay, so what we're going to do is we're going to draw the chord line that is connecting between point A, the first point at the left, and point D, which is the last or the furthest right point, which is this point. And this is, as you can see, the dotted line here. This is what we call it, what? The chord of the primary beam. The chord of the primary beam. Okay? Okay. So that's the point. Now we want what? Exactly. We want to get the relative. We are interested in the relative displacement, not on the absolute displacement. So after drawing the chord, as you can see it here, we are going to measure the distance between point B after settlement and the chord point here. And similarly, we are going to find what is the distance between the point C and the chord point here. So this is from our calculation. If you are going to calculate it, actually we have here, this is 0.75 at point D. So this is considered to be as if a triangle, and then we can obtain these values, which is 0.25 and 0.5 inch at point C, the distance between the original point of the indeterminate beam to the chord point, and from here and from here. This is easy to be obtained. We have here 0.75, and we have like 3 spans here, and all of them, they are 20 feet. So this means that we are the displacement here is going to be 1/3 of 0.75, and here it is going to be 2/3 of 0.75, which is 0.5. So it is easily to be obtained. Then we are going to obtain the relative displacement, which is here 0.375, from where it is 5/8 inches minus 0.25, it is going to give us 0.375. Similarly here is 0.5, so we subtract it from 1.5 inch, then we're going to have 1 inch here, which is the relative displacement or settlement. Okay, so this is what I want you to know now. So our relative settlement is 1 inch at point C and 0.375 at point B. This is our main settlement values now. Okay, this is our main settlement values. Okay, now let's go to the next step. So here, the relative settlements, the specified support settlements are depicted in the figure, as you can see here, using an exaggerated scale. We are just exaggerating here. It can be seen from the figure that the settlements of the supports B and C relative to the chord of the primary beam, which is the line connecting the displaced position of supports A and D, which I said that this is the dashed line here. Okay? Or, so the first one is going to be this value. Okay. Take care, what is the reaction or the redundant direction? It is up, going like this. So this is the positive side for us. And for C, yes, it is up. So this is the positive side. But when we found that when we calculated the relative displacement, we found that it is 0.375 what? Down, going down. This means that we need to use exactly minus sign here. Take care of this. Take care of the sign of the relative settlement. Okay, so we have minus 0.375, and at point C, similarly, we have 1 inch, which is going down, and our support reaction, or the redundant, the sign convention for it is in the going up. Then our delta CR supposedly to be minus here. We need to have the minus, and this is the value that we're going to use. Okay, so this is, I put it as a note here, in which the negative signs for the magnitudes of delta BR. What is the meaning of delta BR? Delta B relative and delta at C relative indicate that these settlements occur in the downward direction, that is opposite to the upward direction assumed for redundance BY and CY. Okay, so we are dealing with the sign convention now, and we already have the idea that, or at least we understand that our redundant, they are heading up, which is the positive sign, the positive direction. Our relative displacement, they are heading down, going down, which is minus, as you can see it here. Okay? Okay. Now let's go to the part which is related to the Comfortability Equation. The Comfortability Equation, which as you can see it here. So now we are going to talk about the point B. Okay? The first Comfortability Equation for point B. Remember that our relative support settlement is going to be minus 0.375. Okay, so here this one delta BR supposedly to be with this value. Okay, and for point C, the second Comfortability Equation, the right hand side is going to be delta CR, which is this value. Okay, so the Comfortability Equation is going to be delta B due to external load, which is uniform load in our case, plus the flexibility coefficient, which means that the displacement at point B due to unit load applied by point B, but we are going to multiply it by our unknown redundant, plus the displacement at point B due to unit load at point C multiplied by the redundant at the point C. This equal to the settlement at relative. We call this is as we said. So this, remember this is the relative support, okay, settlement. Okay, relative support settlement. Okay, this is what we are going to have here. Okay, this is going to be easy for us because we have explained the same example before, so we're not going to spend a lot of time now for obtaining what is delta B node and FBB. You can refer to the previous video or 2 videos before, and you are going to see how we can obtain these values. Okay, just I put it here for you for your information from the example 13.8. So you can find this example, okay, from the previous video. Visit the previous video and you're going to find it. So delta, this is delta B node and delta C node. They are going to be equal, and they are going to equal this value. Okay, so this is delta B node, delta C node. It is going to be here, and remember that going down it is minus, going down is going to be minus. So we are talking about minus value here, and this is a minus value here. And EI, we know EI, then we can obtain the value which is minus 2.24. And for FBB and FCC, they are the flexibility coefficients. They are going to be the same. You can use the beam deflection formulas. Okay, beam deflection formulas. The beam deflection formulas. Okay, so from here you can obtain FBB and FCC. It is easy for you, and substitute with the values of E and I. You can obtain this value, which is going to be 0.0275. Why it is positive? Because they are in the same direction of the assumed redundant. They are going up. take care, this is the FBB and FCC, so they are going up. This means that it is positive. Okay, if this is the primary beam, then the supports for or the elastic shape is going to be something like this, right? This means that going up at point B, for example, this is positive. Okay, but here in this case, delta B node and so on, it was negative. We were using this is the primary beam, and there was something like this, so they were like going down, which is negative. Okay, now the last ones are like FCB and FBC. They are going to be equal because we are applying Maxwell's law. So we are going to find that FCB and FBC, they are going to be equal and positive as well. So they are going to be with the positive sign and having this magnitude, which is 0.0238. Okay. Okay. Now let's go to the next part, next slide. So now the magnitudes of the redundance, which is the magnitude of these redundance, which is CY and BY, we are going to substitute here by substituting the numerical values into the Comfortability equations. So this is the Comfortability equation, and we are going to put our numerical values that obtained from the previous slide with the same sign. This is minus 2.241. FBB, it was positive 0.027. FBC, it is 0.023. Take care, it is positive. Times CY and BY, they are our unknowns here. Okay, equals to the right hand side is delta BR, which is exactly minus 0.375. Similarly, for the second equation, this is the first equation, which is going to be applied at point B, and this is the second equation, which is going to be applied at point C. So here, this is minus 2.24 delta C node, because they are the same, plus, again, sign convention, 0.0238, our unknown BY, plus 0.0272 times our unknown redundant. And here it is minus, as we said, minus 1 inch, because it is going down. Now there are like two unknowns in two equations. We have equation 1 and we have equation 2, and we can solve for our BY and CY. This means that after substitution and solving two simultaneous equations, we can find that BY equals to 122.3, and it is up because it is positive here. But CY, we found that there is negative sign happened or appeared here. This means what? The assumption that we have done before, which we have assumed that CY, if you go back, it was like this, going up. But we found that it gives us minus in the magnitude here at the final calculation. This means that our direction should be reversed. CY should not be up, it should be down. So negative means that tension reaction. Okay, the reaction is going to be tension, and the right direction for this redundant is going to be downward, not upward as we have assumed before. Okay, take care from these small things and tiny details, because really they are going to be important to get and obtain the right answer and make your calculation to be right. Then you need to follow these small tiny things. Okay, now the last step is the reactions and shear and bending moment diagrams. The remaining reactions of the continuous beam can now be determined by equilibrium. It's very easy for you because already we know now BY, it is 122 going up, it's upward. CY is going to be 61, going down, downward. Take care of this. And now for the reactions at A and D, we're going to obtain it by the summation. Very easy for you, you can obtain it taking the moment here. You know this reaction and you know this reaction, then you can obtain dy, and then summation of y equal to 0, you are going to obtain ay 1 point something, and summation of x equal to 0, you are going to find that we do not have any external loads, horizontal loads or reactions, then ax is going to be 0. Okay, so that's the case. and we have all the reactions now. We can draw our shear, and we can draw our shear, and we can draw our moment force diagram. Okay, they are very easy to be drawn. As you can see here, we have like linear variation and then abrupt variation at the reactions, and then another linear here, then abrupt reaction, and then linear value. And whenever that we have linear value for the shear, we are having parabolic distribution or variation for our moment. And here this is the maximum. The maximum moment is going to appear at point C, as you can see with this value. Anyway, drawing the bending moment or the shear and bending moment, this is an easy task and job for you, I think. But now I need to confirm and place emphasis on our main idea for using the support settlement. Please remember well these two important hints that I have mentioned here. They are very important regarding how to obtain the right answer at the end. The magnitude, okay, should be like the magnitude of the settlement should be like measured from the chord, okay, and the sense or the sign convention should be assumed always in similar to, or if it is in the same direction of the redundant, then you are having positive settlement, otherwise it's going to be negative. This actually concludes our today's video regarding how we can use the method of consistent deformation and support settlements. As you can see, it's very easy, simple. Just we have followed the same guidelines of the consistent deformation method, and we found that we can get the straining actions easy, and we can draw the shear and bending moment easily as well. Thank you, and see you in the next video.